Hello everyone, hope you're doing great. Welcome to this recorded session on Introduction to Artificial Intelligence and Machine Learning. In this presentation, we will explore the fundamental concepts and real-world applications of artificial intelligence, often abbreviated as AI, and its key subfield, machine learning. We will also introduce the concept of intelligent agents, a core element in modern AI systems. Whether you're a student curious about the future of technology or a beginner looking to get started in this field, I assure you, you're in the right place. Let us begin with a few simple examples to illustrate the kinds of problems AI can help solve. Consider the case of traffic management on a busy highway such as E311 in the UAE. Using data from cameras, GPS systems, and historical congestion patterns, AI systems can predict traffic jams and optimize signal timings in real time. Another powerful example is medical diagnosis. AI algorithms trained on thousands of medical records can assist physicians by identifying potential illnesses, suggest treatments, or even flagging anomalies in radiology scans. These examples highlight how AI is already making a measurable impact across different domains. In this lecture, we will cover the following key topics: the importance of AI and data mining, a definition and overview of artificial intelligence, along with a detailed look into machine learning and its various types, and finally, an introduction to the concept of intelligent agents. By the end of the session, you should be able to explain how AI systems work, what machine learning really means, and how intelligent agents perceive and act upon their environment. One of the primary drivers behind the recent boom in AI and machine learning is the unprecedented scale at which data is being collected. From social media platforms like X, formerly Twitter, to sensor networks in smart cities, to simulations in climate science, data is being generated continuously and rapidly. The prevailing mindset is simple: collect as much data as possible, as often as possible. The belief is that this data will either serve its original purpose or reveal new, previously unforeseen insights. This explosion of data has made traditional data analysis methods inadequate and opened the door for advanced techniques like AI and data mining. Before we go deeper, let's clarify a key term: data mining. Data mining refers to the computational process of discovering patterns, correlations, trends, or anomalies in large data sets. Think of it as finding meaningful needles in massive digital haystacks, often with the help of algorithms and statistical models. It's a cornerstone of machine learning, and as the volume of data explodes, mining it effectively becomes not just valuable but vital. From a commercial perspective, data mining is essential for staying competitive. Major organizations such as Meta and Amazon deal with petabytes of user activity and transactions daily. Analyzing this data allows them to understand customer behavior, personalize user experiences, detect fraud, and optimize operations. Moreover, with the growing affordability of computer power and storage, companies are under constant pressure to derive actionable insights from their massive datasets. In short, data mining enables smart decision making and offers businesses a significant competitive advantage. In the realm of science, data is not only vast, it is critical. For instance, NASA archives petabytes of satellite data annually. Telescopes gather astronomical observations, while biological labs collect high throughput genetic data. These datasets are often too large and too complex for manual analysis. That's where data mining becomes invaluable. It supports automated hypothesis generation and helps researchers identify patterns that would be impossible to detect otherwise. Whether it is detecting climate change trends, or discovering new drugs. Scientific breakthroughs today increasingly rely on intelligent data analysis. Data mining is the foundation and crucial building blocks of AI. Now that we have explored data mining and the growing importance from both commercial and scientific perspective, it's helpful to take a brief step back and ask, how did we get here? Where did AI begin? And how has it evolved into what we see today? The story of artificial intelligence begins not with machines, but with philosophy and mathematics. The idea of building intelligent systems has been around for centuries, from the mechanical automation of ancient Greece and Egypt to philosophers imagining reasoning machines. The formal field of AI, however, was born in 1956 at a now famous workshop held at Dartmouth College in the United States. Pioneer John McCarthy coined the term artificial intelligence. Mr. McCarthy, along with his colleagues, proposed that every aspect of learning or intelligence could, in principle, be simulated by machines. Around the same time, Alan Turing had already introduced the concept of universal machine and famously posed the question, can machines think? This work laid the foundation for modern computing and the Turing test, which is still used today to assess machine intelligence. The 1950s to the 1970s saw a wave of optimism. Early programs solved algebra problems, played games, and proved theorems. But these systems relied heavily on hand-coded rules, and as tasks grew more complex, they began to fail. This led to what is often referred to as the AI winter, periods in the 1970s and again in the 1980s, where funding dried up and enthusiasm waned. In the 1990s and early 2000s, however, two things changed. First, the rise of machine learning shifted AI from hand-coded logic to data-driven learning. Second, computing power and storage became dramatically more accessible. The result has been an AI renaissance, powered by algorithms that learn from data, adapt in real time, and outperform humans in tasks like image recognition and language translation. As we'll see, today's AI is no longer confined to the lab. It's embedded in our phones, our hospitals, and even our cars. We have seen how AI developed from rules to learning systems. Let's examine how it is being applied across real-world domains from medicine to banking and beyond. Artificial intelligence is not just a research discipline. It is a transformative force across almost every industry. From speeding up drug discovery to detecting financial fraud, AI applications are becoming integral to modern life. According to a CB Insights report, AI startups raised approximately $66.8 billion in 2022, more than double the amount in 2020. The pace of adoption reflects not only enthusiasm but also necessity. Organizations need AI to stay competitive, efficient, and innovative. Some of the key sectors benefiting from AI include medicine, banking, media, agriculture, and renewable energy. Most critical and promising domains is healthcare. The World Health Organization noted that integrating AI into healthcare systems could lead to more informed health policy decisions and more accurate diagnosis. In clinical settings, AI is used to analyze medical images, predict disease progression, and assist in treatment recommendations. For example, deep learning models are already outperforming radiologists in detecting certain types of cancer. Beyond diagnosis, AI is also helping to reduce costs and improve the overall patient experience. Every year, approximately 400,000 hospitalized patients experience preventable harm, and around 100,000 of those cases result in death, often due to diagnostic errors. AI can address this by augmenting the doctor's ability to assess a complex data quickly and accurately. With access to vast historical datasets and symptom patterns, AI models can flag rare conditions, detect inconsistencies in diagnosis, and even recommend follow-up actions. Several healthcare institutions now employ AI-powered decision support systems to minimize human error and save lives. Is notoriously time-consuming and expensive, with some estimates suggesting an average cost of $1.3 billion per drug and a success rate below merely 10%. Currently, drug developments require a minimum time of 10 to 15 years. These large time periods are justified because of the thorough research required before a medicine is available to the general public. However, with the intervention of AI, this time period could be cut down to a maximum of 1 to 2 years. AI streamlines this process by simulating how different molecules might interact, predicting side effects, and identifying promising compounds much earlier in the research phase, therefore dramatically reducing the time required to bring new treatments to clinical trials. A benefit that was evident during the COVID-19 pandemic, where AI played a role in vaccine development and testing strategies for treating illness. It's also about improving how patients experience care. Hospitals are using AI to manage patient flow, reduce wait times, and allocate resources more efficiently. Studies show that positive patient experiences directly correlate with financial success for hospitals. AI helps by personalizing communications, predicting peak traffic in emergency departments, and even automating follow-up care instructions through chatbots or virtual assistants. Application is robot-assisted surgery. These systems are not replacing surgeons, rather they enhance precision, control, and visualization. Robots can carry out minimally invasive procedures with great accuracy, reducing recovery times and post-operative complications. A surgeon might sit at a console controlling robotic arms with millimeter level precision while viewing the surgical field in 3D at magnified resolution. This hybrid model of human expertise and machine precision is revolutionizing operating rooms around the world. AI is driving significant innovation in banking and risk management. According to a 2022 report, over 50% of financial institutions are using AI for risk assessment, fraud detection, and personalized financial services. For example, machine learning models can instantly flag suspicious transactions, evaluate loan applications in real time, and adapt credit scoring system based on evolving data. The potential cost savings from these technologies is estimated to reach up to $400 billion across the global banking sector. And media industry, AI is fueling content creation, personalization, and visual effects. From generating synthetic voices to enhancing CGI in film production, AI tools are reshaping how stories are told. The AI in media market is projected to grow from around $11 billion in 2021 to nearly $100 billion by 2030. Streaming services like Netflix and Spotify already use AI to predict user preferences and generate tailored recommendations. Holds immense promise for solving some of humanity's most pressing challenges, such as developing sustainable energy solutions, modeling and mitigating the impacts of climate change, improving food security through smarter agricultural systems. These global problems are data rich and incredibly complex. making them ideal candidates for AI-driven intervention. History of artificial intelligence and its current relevance. Now let's begin to unpack what it actually is and how it relates to machine learning. Capability of machines to simulate human intelligence. That includes abilities such as learning, reasoning, understanding language, and even perceiving the environment. Think of AI like a student. The goal isn't to memorize exact answers, but to develop the capacity to understand, infer, and adapt. A smart assistant like Siri or Alexa may seem simple on the surface, but behind the scenes are layers of AI systems interpreting speech, identifying intent, and generating responses in milliseconds. Learning. Machine learning is the most practical and widely used subset of AI today. Here's an analogy to maybe understand it better. Imagine teaching a child to recognize animals. You could write down rules like if it barks and wags its tail, it's a dog. That's like traditional programming. But with machine learning, you just show the child hundreds of pictures of dogs and cats, and over time, they begin to learn the difference based on patterns. ML does the same thing, but with data. Traditional programming relies on if-then logic written by developers to produce specific outcomes. While these are effective for simple tasks, it struggles with complex problems involving numerous variables or unpredictable conditions. ML overcomes these challenges by learning from the large data sets. It's especially useful when a task is too complex to hand code manually, for example, recognizing emotions in a face or predicting customer behavior. While we have discussed both artificial intelligence and machine learning, it is important not to confuse the two. AI is the broader field, let's say like the universe in this case, a broader field in which machines should be able to carry out tasks in a way that would be considered smart. This includes perception, reasoning, decision making, and learning. To put it in simpler terms, artificial intelligence is a technique which enables machines to mimic human behavior. On the other hand, machine learning is one galaxy within that universe. It specifically focuses on algorithms that allow machines to learn from data and improve over time. The emphasis is improve over time. This is what distinguishes artificial intelligence from machine learning. And it does this without being explicitly reprogrammed. Deep learning, which is a concept we'll get to soon, is like a solar system within that galaxy based on special type of algorithm called neural networks. I hope this representation of the slide gives you a much better understanding of the concept and how they are related. To further explore and understand machine learning, we need to have an idea of the different types of machine learning, which are designed for different types of problems. The five main types we'll explore are supervised learning, unsupervised learning, semi-supervised learning, reinforcement learning, and deep learning. Let us examine each of them, starting with the most common, supervised learning. In supervised learning, the system learns from a manually labeled dataset. Labeled dataset forms the foundation for this type of machine learning. Each data point in the dataset has an associated correct answer or label. For example, in image recognition, each image would be labeled with the object it contains. Let's say a photo of a cat would be labeled as cat. The algorithm learns by analyzing the relationship between the input data and the corresponding labels in the training set. It identifies patterns and relationships that enable it to predict outcomes for new, unseen data. Supervised learning is commonly used for two main types of tasks. One is regression. Regression is mainly used for predicting a continuous value. Let's say, for example, predicting house prices based on features like size and location of the land. And another type is classification. That is to categorize data into predefined classes, like classifying mails as spam or not spam. Imagine a teacher giving a student a math problem along with the correct answer. The student keeps practicing until they can solve new problems using what they have learned. In the same way, a supervised learning model might be trained to analyze and capture sentiments from a text data. This type of learning is widely used in applications like credit scoring, image classification, and speech recognition. Supervised learning involves two primary phases. The first phase is a training phase, and a second phase is the prediction phase. The objective of the training phase is to enable the machine learning model to learn the underlying patterns and relationships between input features and their corresponding target outputs. As you can see in this picture, the machine is fed some label data such as rectangle, circle, triangle, and hexagon. It understands the underlying patterns and relationships between the input and the labeled data to form patterns and connections and distinction between the different inputs. The second phase is a prediction phase. The objective of the prediction phase is to use the trained model to make predictions on new unseen data. And as you can see in this picture again, the prediction phase here, the model is fed raw unlabeled data, and according to the pattern it has already formed, it predicts an output. Unsupervised learning is a type of machine learning where algorithms learn from unlabeled data, uncovering hidden patterns and structures without explicit guidance. Unlike supervised learning, which uses labeled data to train models for specific predictions, unsupervised learning focuses on discovering inherent relationships and insights within the data itself. So basically, the goal is for the algorithm to identify patterns, structures, and relationships within the data without human intervention. Unsupervised learning is often used for exploratory data analysis, where the goal is to gain a better understanding of the data and potentially discover previously unknown insights. Unlike supervised learning, again, there is no any targeted variable or a target variable. Let's say, for example, it's like walking into a room full of strangers and trying to figure out who might be friends based on body language and proximity without being told anything explicitly. This type of learning is used for market segmentation, customer profiling, document clustering, and anomaly detection. Common techniques within supervised learning are clustering, dimensionality reduction, anomaly detection, and association rule mining. Among these techniques, we'll be elaborating more on clustering and association rule mining. As you can see here, the model is given data without any prior guidance or reference, making it an unlabeled data. However, the machine identifies patterns and structures to successfully group together like objects, hence distinguishing one shape from another. One of the most common unsupervised learning technique is clustering. Clustering is about grouping data points based on similarity. Picture a scatter plot of thousands of dots representing customer behavior, for example. The algorithm identifies groups of dots that are close together and assigns them into clusters. Each cluster might represent a different customer persona or shopping pattern. To better understand what is a cluster, visualize them as groups of objects with similar attributes or groups of identical objects. Different similarity metrics can be used to form these clusters, like distance in Euclidean space, frequency, or correlation. These groupings can then inform business decisions like targeted marketing. As you can see in this image, clustering has grouped similar fruits together based on their features, such as color, shape, or size, without knowing what the fruits are. One cluster has apples, another has pears, and the third has strawberries. The algorithm does not know these are apple or pear or strawberry. It just notices that certain fruits are more similar to each other than the rest and groups them accordingly. This is the power of unsupervised learning. Even without labels, it can find meaningful patterns in data. Later, once the clusters are formed, we can go in and interpret what they mean, like realizing that this group is mostly apple, for example. To summarize, clustering mainly helps with understanding patterns, for example, grouping genes with similar biological functions, or just like the previous example we saw where identical fruits were grouped together. Clustering also helps with reducing data size. It does that by summarizing it into meaningful clusters. And furthermore, clustering also helps establish a right target audience by segmenting customers to serve them more efficiently. A real world example to that would be any e-commerce platform. Let's say Amazon, for example. If you have noticed previously, when you buy a product before checking out, you might be suggested similar products as well. This is because you have been added to a cluster of people who might have bought products in the same range. Let's say when buying a blender, you may be grouped into a health conscious kitchen shopper cluster, triggering suggestions for protein powder or recipe books. Now let's look at another type of unsupervised learning technique, association rule mining. Association rule mining is about discovering relationships between variables in large data sets, particularly when those variables occur together frequently. As you can see in the slide, a store has tagged some of its products in some based on some pattern. And from the picture, it can be inferred that customers who buy banana often also buy carrots or potatoes. This does not have to occur always, but frequently enough that it becomes a statistically relevant pattern. This kind of rule helps businesses make data-driven decisions. Mathematically, these rules are evaluated using metrics such as support, confidence, and lift. Since the mathematical perspective of association rule mining is way above the scope of our discussion today, let's move on. Association rule mining is widely used in market-based analysis. As the example we said before, let's say using association rule mining, a store could learn that customers who buy bread and eggs also tend to buy butter. This insight can then guide shelf placement strategies, cross-selling bundles, personalized offers on e-commerce platforms. Let's say platforms like Amazon, showing frequently bought together. When if you are buying a phone, you're recommended a charger as well as a screen protector. And that is a classic example of association rule mining in action. Beyond retail, association rule mining is used in medical informatics to discover co-occurrences between symptoms, diseases, and treatment outcomes. For instance, analyzing hospital records might reveal that patients with high blood pressure and elevated cholesterol levels have a high likelihood of also developing type 2 diabetes. These rules don't prove causation, but they provide useful hypotheses for clinical research and diagnostics. Again, now let's move into semi-supervised learning, a hybrid approach between supervised and unsupervised learning. In many real-world cases, we have a small amount of labeled data and a large amount of unlabeled data. Labeling is expensive. It often requires human experts. For example, tagging medical x-rays or annotating speech recordings. Semi-supervised learning allows us to train a model with labeled portion and then let the model label the rest based on patterns it has already detected. The algorithm begins by identifying clusters or density-based structures in the unlabeled data and then uses the few labeled points to guide or anchor the interpretation. As you can see from the slides, first a model is trained using labeled data, a small set of labeled data. This trained model is then used to predict labels for a large set of unlabeled data. This labeled large set of unlabeled data forms a pseudo labeled data. This for pseudo labeled data along with the labeled data is used to retrain the model and enhance its capabilities. This approach, the approach of semi-supervised learning, is gaining significant traction in fields where data is plentiful but labeling is not scalable. For example, let's say tagging thousands of cats and dogs photos for image recognition, or sentiment analysis for product reviews in natural language processing, and also finding anomalous behavior in system log for cybersecurity. By minimizing the need for labeling data, semi-supervised learning strikes a practical balance between performance and resource constraints. Reinforcement learning is a machine learning paradigm where an agent learns to make decisions in an environment to maximize a cumulative reward. It's a type of learning through trial and error, similar to how humans learn from experience. The agent interacts with the environment, taking actions and receiving feedback in the form of rewards or penalties, and adjusts its behavior to optimize its performance. So, how reinforcement learning actually works is the agent starts with an initial policy, which could be random or based on its prior knowledge. It interacts with the environment by taking action based on its policies. The environment provides a reward or penalty based on the action that has been taken. The agent updates its policy based on the received reward, aiming to maximize the cumulative reward over time. This process continues iteratively, allowing the agent to learn the optimal strategy for achieving its goal. As illustrated here, the agent senses the environment, takes action, and updates its strategy based on the reward signal. A useful analogy could be training a dog. If it sits when told, you give it a treat. If it runs away, you ignore or correct it. Over time, the dog learns the behavior that maximizes its reward. The agent behaves the same way as well. Reinforcement learning powers some of the most advanced AI systems. It's used for motion planning and control in robotics, and reinforcement learning strategies optimize trading over time in finance. Now we arrive at one of the most revolutionary technologies in AI, deep learning. Deep learning is a subset of machine learning based on artificial neural networks, which are inspired by how the human brain works. A neural network consists of layers of interconnected neurons, which are simple computational units that transform input into output step by step. These input, this networks typically consist of input layer, which receives the raw data, hidden layers, where feature extraction and transformation happens, and output layer, which generates the final prediction or decision. Deep learning is what powers speech recognition, like Siri or Alexa, facial recognition systems, self-driving car vision systems, and machine translation like Google Translate. As we have discussed before, deep learning is a subset of machine learning. A key distinction between classical machine learning and deep learning is in feature extraction. In traditional ML, the engineer must manually extract and select features, for example, shape, color, or texture in an image. But in deep learning, the network learns which features matter during training. Think of it in this way. ML is a person who asks, tell me what to look at, while deep learning is a person who says, I'll figure out what matters myself. This automatic feature learning is what makes deep learning so powerful, especially for high dimensional data like images, video, and audio. Let's zoom in a bit on feature extraction. Imagine you're building a model to classify handwritten digits. Raw pixel data is messy, so a machine learning model first extracts numerical features such as stroke direction, number of loops, aspect ratio. These features then feed into the algorithm to help distinguish, let's say, a 6 from an 8. Good features increase accuracy, poor features confuse the model. In deep learning, convolutional neural networks perform this process automatically. They detect edges, shapes, textures across multiple layers. We have now explored different types of machine learning, from supervised and unsupervised learning to deep learning. But how do we actually build a machine learning system from scratch? Let's walk through a simple example that illustrates the entire workflow. Imagine we want to build a system to detect spam emails, a classic beginner-friendly machine learning problem. We will follow the basic life cycle of a typical ML project, which includes defining the problem, gathering data, pre-processing it, training a model, evaluating results, and finally deploying the system. The first step is always to define the problem or the task in hand. Our task here is binary classification. In other words, classification of email as spam or not spam. The second step is data collection and preparation. To do this, we need to obtain a dataset containing labeled messages, such as emails classified as spam or not spam. Once we have collected this data, we need to clean the text data by performing tasks such as converting all text to lowercase, removing punctuation, special characters, and numbers, and also removing stop words, which are common words like the, is. They don't carry much meaning for classification. Finally, we need to apply stemming or lemmatization to reduce words to their root form. The third step is feature extraction. Transform the clean text data into numerical features that a machine learning model can understand. Common techniques for this include bag of words, which represents text as a collection of word counts, ignoring grammar and word order. There is another technique as well, which is term frequency or inverse document frequency, which assigns weights to words based on their frequency in a document and their rarity across the entire dataset, giving more importance to distinctive words. So finally, by the end of the third step, we have transformed the text into a numerical format, which can be further processed or interpreted by the machine learning module. So now that we have our data ready, the next step is to choose a model and train that model. To begin with, we split the dataset into training and testing sets to evaluate the model's performance and unseen data. A typical split of 80% for training and 20% for testing is ideal. Next, we need to choose a suitable classification algorithm. For spam detection, common choices are naive Bayes and logistic regression. Naive Bayes is known for its effectiveness in text classification, while logistic regression is a linear model for binary classification. Now all we have left to do is train the selected model using training data. We feed the model the email data and its labels. The model learns patterns, such as spam emails often containing phrases like limited time offer or click now will be differentiated from a not spam email. By the fifth step, you have almost completed your first machine learning project because now we have proper results and outputs from a machine learning module which just needs to be further analyzed. That is done in the fifth step, model evaluation. In this step, we evaluate the trained model's performance on the testing set using metrics such as accuracy, precision, recall, and F1 score. Accuracy is the proportion of correctly classified messages. Precision and recall are very closely related and only differ by a small margin. Precision is the proportion of correctly identified spam messages among all messages predicted as spam, while recall is the proportion of correctly identified spam messages among all actual spam messages. To better understand what is precision and recall, let's take some examples. If a filter labels 10 emails as spam and 9 of them are actually spam, the precision is said to be 9 out of 10 or 90%. This means this filter is quite accurate when it labels an email as spam. Now, if there are 20 spam emails in total and the filter catches only 15 of them, the recall is said to be 15 out of 20 or 75%. This means the filter could be better at finding all the spam emails. After the model evaluation, if the results are poor, we might try a more complex model like random forest or even neural networks. The sixth and the final step is deployment. Once satisfied with the model's performance, it can be used to predict whether new unseen messages are spam or not. We can deploy it as a filter in an email service, and we can continue improving it using feedback from new emails. And like that, we have built our first machine learning project. This cycle of define, prepare, train, evaluate, and deploy is the foundation for almost every ML system you will encounter, from fraud detection to self-driving vehicles.
Discuss the building blocks of AI and what is artificial intelligence and machine learning in detail. Now let's venture into another core concept of artificial intelligence, which is intelligent agents. An agent is which is intelligent agents. An agent is any entity that perceives its environment through sensors and acts upon it using actuators. Think of it as self-contained system with three core functions: sensing, which is gathering information about the environment; thinking, which is making decisions or processing that information; and finally acting, taking appropriate actions to achieve a goal. Intelligent agents may exist in physical forms like robots or digital ones like chatbots or recommendation systems. The intelligence comes from agents' ability to make decisions that improve its performance over time. Now let's go deeper into how an agent op- Now let's go deeper into how an agent operates. Basically, an agent comprises of three parts: sensors, actuators, and effectors. Sensors detect changes or input from the environment. Actuators convert decisions into physical or digital ones. Effectors are the output mechanism, the parts of the agent that actually carry out the functions. Understanding these distinctions help us analyze any AI system from a structural perspective. For example, in a robot, a camera or LiDAR system might serve as a sensor. This is because it detects changes in the environment, which are inputs to be further processed. Motors and gears act as actuators because it converts this input digital data into physical actions. Wheels or arms serve as effectors that move or interact with objects. These are the parts that actually carry out the actions to be performed. The agent processes sensor data, makes decisions, and executes those decisions via actuators. This loop repeats continuously. As you can see, intelligent agents bridge both hardware and software layers, from sensing data to executing logic. Agents can be found across three form categories. The first and the foremost is always human agents. Yes, we ourselves are intelligent agents. Our eyes and ears act as sensors, our muscles are actuators, and our actions do affect the environment. The second form of agents are robotic agents. These use cameras, rangefinders, gyroscopes, and other sensors to navigate their environment. Servos and motors serve as their actuators. The third form of agents are software agents. These exist entirely in the digital world. A recommendation engine or a spam filter senses data input and acts by returning personalized results. All three of the agents follow the same sense, think, act paradigm, but just implemented through different media. While human agents are biological, robotic agents are mechanical, and software agents are computational. Now let's apply our Now let's apply our understanding through real-world examples. In the next few slides, we'll analyze various intelligent agents by identifying their environment, which is what surrounds them, sensors, how they perceive that environment, and finally actuators and or effectors, how they act upon it. This exercise helps clarify how AI systems are structured in practical use cases. I recommend you pause the video after each example to think through the agent breakdown yourself before continuing. Let, let's start with self-driving cars, one of the most ambitious applications of AI. The environment for a self-driving car are the roads, traffic signs, other vehicles, and obviously pedestrians. The sensors in this case are the cameras, radar, GPS, sonar, speedometer, and accelerometer. These sensors provide the agent with valuable information on the environment, which are inputs to be processed later. Actuators or effectors in this case are the steering, acceleration, braking systems, and signal lights as they help the agent implement actions based on the provided input. As shown in the diagram, the car constantly senses its surroundings, makes navigation and safety decisions, and carries out physical movements in real time. It uses advanced algorithms including computer vision, sensor fusion, and reinforcement learning to adapt to the ever changing and dynamic road conditions. Self driving cars are some of the most complex intelligent agents in the world, combining all elements of AI. Let us consider an autonomous cleaning robot like a Roomba. The environment for this particular agent are rooms filled with furnitures, walls, floors, and carpets. Sensors needed here would be dirt sensors to understand how much dirt has been accumulated and to decide whether to clean or not. Bump sensors, which are needed to avoid obstacles. Cliff sensors to avoid edges, and infrared wall detectors. Actuators will be wheels, brushes, and suction fans. The robot navigates rooms, avoids obstacles, and cleans based on detected dust levels. As you can see, this is a relatively simple agent, but even here, AI plays a role in path planning, area coverage, and obstacle avoidance. Finally, let's look at a bin picking robot commonly used in manufacturing and warehouse automation. The task here is to pick random parts from a bin and orient them correctly for the next step in production. The environment for this agent is conveyor belts, metallic or plastic parts in containers. And sensors needed would be cameras, joint angle sensors, and sometimes LiDAR. Actuators are multi-joined robotic arms, suction grippers, or vacuum tools. These robots rely heavily on machine vision to detect object positions and shapes, and on inverse kinematics to compute the best movement path. They are designed for precision, speed, and high repeatability, often working alongside humans in collaborative robotic systems, which are called as cobots.
We have just examined how intelligent agents function, sensing their environment and taking actions towards a goal. But what comes next? Let's take a look into the future of AI. Artificial intelligence is not standing still. It is a field in rapid transformation, evolving faster than almost any other area of technology. Let's explore five major trends shaping the next phase of AI development. Artificial General Intelligence, or AGI. Today's AI is known as narrow AI, systems trained for one task only, such as translating languages or recognizing faces. AGI, or Artificial General Intelligence, refers to machines that possess broad cognitive abilities that are capable of reasoning, planning, and adapting across a wide range of tasks like a human. While AGI is still theoretical, companies like DeepMind, OpenAI, and Anthropic are actively exploring architectures that can generalize knowledge. The implications are profound, raising both technical and ethical questions about the boundaries between machine and human intelligence. Explainable AI, or XAI. As AI systems influence decisions in healthcare, hiring, finance, and law, there's a growing concern around transparency and accountability. Explainable AI focuses on building models that can be understood and interrogated. Instead of treating AI like a black box, XAI answers questions like, why did this loan get rejected? Why did the model flag this patient for further screening? Techniques like LIME and attention visualization are making AI more interpretable and therefore more trustworthy. As discussed previously, beyond business, AI is increasingly being used to address global challenges. In agriculture, AI-powered drones monitor crop health and optimize irrigation. In public health, machine learning helps track diseases outbreaks and optimize vaccine distribution. In climate science, AI predicts weather patterns, tracks deforestation, and simulates carbon reduction policies. Organizations like UNICEF and UN are funding AI for good initiatives, especially in developing countries. AI governance, ethics, and regulation. As AI becomes more powerful, the question is not just what it can do, but what it should do. We are seeing the emergence of AI regulatory frameworks, the European AI Act, or the US executive orders on AI safety, and new laws in countries like the UAE, Singapore, and India. Key ethical concerns include bias and discrimination in algorithms, data privacy, and weaponization of AI. The future will depend on building AI that is responsible, fair, and aligned with human values. AI convergence with emerging technologies. AI is also intersecting with other cutting-edge domains. Quantum computing could enable vastly more powerful models for AI. Blockchain with AI promises secure, decentralized decision making. AI with biotech is unlocking personalized medicine and protein folding. The lines between disciplines are blurring, and this convergence will lead to entirely new industries. In short, the future of AI is not just about faster algorithms. It's about building systems that are general, explainable, ethical, impactful, and interconnected. As students and early professionals, the skills you build today will shape how these systems are designed tomorrow.
As we come to the end of this session, let's take a moment to reflect on what we have covered. We began by understanding why artificial intelligence and machine learning are becoming indispensable tools across industries and scientific disciplines. We explored the types of machine learning, including supervised learning, unsupervised learning, semi-supervised learning, reinforcement learning, and deep learning. We also introduced the foundational idea of intelligent agents, systems that sense, think, and act autonomously. And we analyzed real world agents such as self driving cars, cleaning robots, and software assistants. I believe the core insight you gain from today's lecture is that artificial intelligence is not just about building smart machines, it is about designing systems that can learn, adapt, and improve in complex data rich environments. AI is already shaping how we interact with technology, how decisions are made in business and medicine as well, and how we address global challenges from sustainability to healthcare. And believe me, this is only the beginning. For those of you, for those of you who are just getting started in this field, I encourage you to explore hands-on projects, open datasets, and further introductory courses in AI and data science. Platforms like Google Colab, Kaggle, and MIT OpenCourseware offer valuable free resources to deepen your understanding. And as you move forward, always remember, the goal of AI is not to replace human intelligence, but to extend and amplify it. Thank you for joining me in this introduction to artificial intelligence and machine learning. I hope this session has not only explained the fundamental concepts, but also sparked your curiosity to explore further. Feel free to revisit any section of this recording and continue learning at your own pace. Once again, thank you for your time, and I wish every one of you all the very best on your journey into the world of AI.